My name is Joseph Shelby. I'm a senior DevOps engineer here at Asurion. Recently christened. My former title was senior infrastructure engineer. My day-to-day job is on the platform architecture team. So we focus primarily on upcoming new technologies, auditing them, establishing standards for their governance and things within the organization. Specifically, I'm working on a couple of different projects right now for data analysis in AWS, as well as a chatbot platform that's going to be an enterprise class ubiquitous platform across our environment. So before I begin, I'd like to give you a why you should listen to me slide. I always go to these presentations and I find myself wondering, so who is this person again? What are their qualifications and everything? So I thought I'd head that off at the pass. So my background is that I've developed several REST APIs for internal consumption for different platforms and products at our company. I've also have some experience consuming and transforming data from various sources, various databases, various third-party REST APIs. For those of you, I know this is a beginner's course, but for those of you who are a little more seasoned, you know that there's a lot of variance in the type of data that can come from these structures and things like that, and that requires a lot of care and feeding and can require a lot of governance and things like that. And then I also love data structures. They're really interesting. It reminds me a lot of Legos when I was a kid. You take something small and you build something really, really cool and interesting out of it. So before I get too far into this, with the understanding that this is a beginner level course, I wanted to set out some goals and some expectations and things like that. There will be some terminology. I will try to keep the syntax as straightforward as I can, but if you have questions, feel free to interrupt me, raise hands, things like that. I'm happy to clarify where needed, but I'll try to keep that to a minimum as much as I can. So the goals of this exercise are to give you a basic understanding of what a data structure is and why they're important, what their use cases are. I also want to walk you through a technical definition of various data structures and their implementation in three popular programming languages. Now, I want to pause for a second. The reason why I'm focusing on that is because I know when I was a beginning developer a few years ago, one of the big issues that I had, because I was largely self-taught, is that I learned things the Python way. I learned what Python calls an array. I learned what Python calls a dictionary. Oh, sorry, I'm skipping ahead. And so I wanted to make sure to clarify the differences when we say what a technical definition is versus a real world or a practical definition. So that's why I wanted to bring that up. So some key terms and definitions just to get us started. So first off, we're going to talk a little bit about data types. A data type is just a classification. It's just a bucket. It's just something that allows you to classify data in some way. So think of strings, integers. Those are two very popular, pretty standard examples that are common across all programming languages. We're also going to refer to things that are statically typed. Now, statically typed simply means that we're defining a data type ahead of time. So we're saying that this piece of data is a string, this piece of data is an integer, and so on. We're also going to refer to things that are dynamically typed, meaning that we don't define them ahead of time. We don't say this is a string. We don't classify it in some way. Python is an excellent example, and one that I'm sure a lot of you are familiar with, of a dynamically typed language. You'll also hear me use the term primitives. Primitives are, simply put, a built-in artifact in a programming language. Some of the nuances and some of the definitions can vary between developers and things like that, but here it will just simply mean something that is inherent to the programming language of choice, something that the language designers have created, not something that we introduce after the fact. You'll also hear me refer to the term elements quite a bit. Elements are a key component of most data structures, and this time I'm going to define them as simply something inside of a data structure to avoid a lot of the confusion and things like that. So whenever you hear me refer to something as an element, it's just simply something inside of a data structure. So first off, so to begin, we're going to first talk about what is a data structure. So in order to know what a data structure is, it's sometimes helpful to know, well, what is data? What do we refer to data as? So Webster's defines that as information in digital form that can be transmitted or processed. To break that down a little bit and make it a little bit cleaner, it's anything, I'm going to define it here as anything, any artifact generated by your software. I'm a big fan of the term artifact. I think it's a really nice generic catch-all that comprises a lot of different things, and it really helps when you're talking about different programming languages and things like that. So that's what data will be referred to as here. So the next question then you have to answer is, well, why do you want to store data? What's the point of storing it? Well, frankly, you might need it later. The program is running in real time, and you might want to take that integer or that string that you've created and refer to it at some other point in your program. That's a little bit beyond the scope of this lecture. If you have questions about that, feel free to come up to me afterwards. I'd be more than happy to go through those, but I do want to keep this pretty focused on data structures. You can think of these sort of like an ephemeral database for software artifacts. So what I mean when I say ephemeral is that it doesn't persist. It doesn't, if you close the program, it goes away. It's no longer available. If you want it to persist, you have to put it in something like a database, or you have to write it to a file on disk. Once it's gone, it's gone. Once the program concludes, and that's a distinction that I'll talk more about here in a moment. So let's talk about some basic data structures. So as I already mentioned, there is a lot of inconsistent terminology and a lot of implementation differences. That's what I classify as theory versus reality. So a good example, Python refers to lists as lists. Well, they're technically linked lists, but Python chooses to shorten that and refer to them as lists. So one thing that I find extremely important when you're learning any programming language is to read the language specification. Just get yourself a cup of coffee, get yourself a cup of tea, take a couple of hours, go through the language spec, understand what goal the designers had in mind, understand why they did the things that they did and they made the decisions that they did, and that will help you a lot in understanding these nuances and things. So when you go from something like JavaScript to something like Golang, you're able to make that transition a little more easily and a little more fluidly. So the first data structure that we're going to talk about are variables. Now I know these aren't technically a data structure, but they are still worth mentioning because they are something that you can use for storage. And a lot of times in the interest of simplicity, they're the best option. Not every time, but a lot of times they can be very useful. We're also going to talk about arrays, linked lists, stacks, and queues. So these are all linear data structures that are designed and intended for fast data retrieval. We're also going to refer to hashes. Hashes are key-based storage that make things easier for humans, and I'll show you more about what I mean on that in a second. But suffice to say now that they're probably the one that you're going to see the most and that you're going to be the most familiar with over the course of your development career. So let's start with variables. And this is my first one of these presentations since college, so I'm not brave enough to try live coding, so you're just gonna have to deal with the nice, I did write these, I promise, but you're just gonna have to deal with the screenshots there. If we decide to get interesting later, I might try some, but for now we'll stick to this. So first off, let's talk about what a variable is. So simply put, a variable is a bucket or to put data or a name that you want to call an artifact. Python is a little bit different because it refers to them as names, but a lot of programming languages, especially older programming languages like C, still have the concept of an empty variable, something that you define ahead of time and you put data in later, and I'll show you examples of that in just a second. Something when you're dealing with variables that's very important to remember is that there is a difference between assignment and declaration. Assignment is when you actually take data and put it into a variable. Declaration is when you simply bring the variable into being. What the technical term is instantiate the variable. And so those are two differences there. So why should you use variables? For the first reason is that it prevents hard coding. One thing that you see that can happen early on in your development career is that you may just simply say, well, I'm only going to use this once, I'm going to put this string in there and then walk away. That's not a great habit to develop. You really want to start building good behaviors early, and you really want to make sure that you're making liberal use of names and things like that. It also prevents from extensive refactoring, and the example here, which we'll get into a little bit more in a second, actually has a bug in it that we could fix through refactoring with a variable that I'll walk you through momentarily. So as I said, it allows for code reuse, it allows for extensibility. Those are two somewhat technical terms that essentially mean that when it's time to go back and revisit your application 3 months after the fact and 6 months after you initially wrote it, and now Google has decided that they want to be called alphabet.com, and you're sitting there at midnight trying to figure out all the places where you wrote alphabet.com instead of putting it in a URL, That's the kinds of situations that variables can help to prevent. It also keeps you from having to remember what you called something. I won't speak for anyone else in this room, but I'm a very lazy developer. I don't like to remember things. I like to have them put in front of me in a way that I can understand easily. So this prevents you from having to remember, for example, www.google.com and simply call it URL. And that is also important because, remember, you're not the only person reading your code. You're not the only person who's going to be working on these projects and things. So what I call something may not be the same thing as what you call something. So I've heard this said before, and I completely agree with this. One of the hardest things in development is naming something. I cannot tell you the amount of time I have put into sitting there just staring, and my boss probably thinks I'm crazy, and I'm just sitting there staring at a monitor like, that name's not quite right. Because you have to think about who else is going to be reading this. You have to think about, maintainability and things like that. So I don't want to overwhelm you, but those are some things that do come up in your development career that when you start building those practices early become really helpful later. So as an example, let's talk about what's easier, a URL or a name for a URL. So like I mentioned a few minutes ago, let's see if this has, oh wait, I don't have the viewer, never mind. There's actually a really cool feature on PowerPoint where you can do laser pointer if you're doing split screen view, which we're not, so you get my finger. So as I mentioned earlier, there is a bug in this program. So for those of you who are familiar with the request library, you'll know that the request library wants you to append your URL string with HTTP. As it's written right now, this program will not run. It will generate an exception. Now, this program here, where I'm using variables, is very easy to go and update. I literally change line number 6, and that's it. If I want it to be google.com, or I want it to be Amazon, or I want it to be anything else, all I have to do is change line 6. Now let's go down here to line 14 without variables. So here you can see I've hard-coded www.google.com, and then you can see down here I've done the same thing rather than replacing it with a variable. So the net result of that is, as written, this code has to be updated twice. Just these short little tiny program, I already have 2 changes that I have to make, and I have to remember where those changes are. Or I have to let the interpreter or the compiler tell me, hey, this isn't right, go fix it. And now I'm spending a lot of time and a lot of effort updating things when I could have simply moved in a new line and walked away. So that's an example of why it's very critical and very important to use variables. Now, as I mentioned earlier, they can also be used for storage. So we can talk a little bit about some of the linguistic differences in variable implementation, and this starts to get into the way that this is going to be structured is I'm going to present you with the technical definition and sort of the generic overview first, and then we'll get into the meat and potatoes of the actual language nuances. So let's start with Python. It's a pretty well-known, pretty widely used programming language. So Python generally refers to variables as names, at least in my experience. And that's because they don't really support a standalone variable in the way that some older languages do, and we'll get more into that in just a second. But you can think of it simply as a name that's assigned to some value. So in the preceding example, URL was assigned to the name www.google.com. Python is dynamically typed, so like I said earlier, that means that I don't have to remember that whenever I pass in a URL that it needs to be a string and that I have to define it as such, and I have to do some pre-work ahead of time. There are reasons that that's a good thing and there are reasons that that's a bad thing. That's beyond the scope of this talk, but again, if anyone has any questions or wants to know more, I'm happy to go on and expand on that at length. So as I mentioned, there's no advanced declaration. You only get the ability to do an assignment statement. JavaScript is very similar. My understanding is that it is an untyped language. My JavaScript skills are not as strong as some of my other languages, but that's my understanding, is that it is considered an untyped language. And what that means is that it doesn't necessarily care what your data is. It's going to try to do something with it no matter what it is. So in JavaScript, you can declare a variable ahead of time, or you can declare and initialize it at the same time. So let's take a look at what that looks like. So let's say that I defined a variable called message. Now note there's no type, there's nothing here. I've literally just created an empty bucket that's called message that I can put something into. And that's exactly what I've done here. So at line 9, I've said message equals this string, which is hello world. Now if I were to print this, I would receive the string hello world sent back to me as the contents of that variable. I don't get message, I get whatever's stored inside of message, and that's a very key distinction. And this is an example of a simultaneous declaration in assignment, so it's a little bit of a shortcut. Sometimes we refer to that in the tech world as a syntactic sugar, if you've ever heard someone say that, and that's simply a methodology by which you can do something differently that doesn't necessarily have any net improvement of the performance of the program, it just looks cleaner. And there are a lot of times when that's very important because, again, readability is extremely valuable when you're doing development. So as you can see here, we've declared the variable and we've also initialized it with its contents. And then again, if we were to print this here, you would see the same string echoed back to you on the terminal or whatever, wherever you're using to display that. Now, my last example is from Golang. Golang is a very, very new language. I'm very partial to it, again, for reasons that I can expand on later. It's what's known as a statically typed language. So like I mentioned earlier, that means that I have to specifically tell the program ahead of time how I'm going to use the variable that I'm creating. So for instance, here at line 17, it looks similar to JavaScript except for this little piece right here. And this is that typing. This is that static typing that I was mentioning earlier. So I have basically said here, I have a variable message. There's nothing in it yet, but when I put something in it, it's going to be a string. Now the benefit of this is that if I try to put an integer in here, for example, the program's going to say you can't do that. That's not the correct type. So at line 18, you can see that I do have the variable message. I don't have to redeclare it or anything like that. I've already done that. So I simply say, this variable message is going to contain this string hello world. And then if I were to print that, again, this is syntactically correct for Golang, I would receive back the hello world string on the command line. So functionally, not very different from Python, not very different from JavaScript in terms of the output, but very different in how they arrive at the output that they're creating. And then another interesting nuance of Go is that you can do the same thing as you did in Java. You can actually do what they call a shortcut assignment, which is you can declare a message and assign it a string. And then Golang is smart enough to say, oh, you handed me a string. I'm going to assume that this variable is intended to be a string, but that's going to be that way from now on. So if I were to come back later and say, well, now I want my message to be any arbitrary string, hello earth instead of hello world, for instance, it would have to be represented as a string, otherwise the compiler would still yell at me and say you can't do that. So once that assignment's made, it's set in stone, so to speak. Golang also allows you to do shortcut assignment operators, very similar to this, but again, a little bit of syntactic sugar to make it a little cleaner and a little easier to follow. So let's now go into linear data structures, arrays, lists, stacks, and queues. Now, again, I want to stress that this is a generic overview of these data structures. This is not specific to any one particular language. So first off, let's talk about what is a linear data structure. So a linear data structure is simply a sequential structure that holds inserted data or elements and is traversed in a linear fashion. Now, there's a lot more to it than that. It's much more complicated in terms of the implementation. In the interest of brevity, I chose to not go into a lot of those details and things, but if you have interest in learning more about that, I have a book that I'll talk a little bit about at the end that's really, really good at going at a very high level overview of some of the really, really in-depth details about what those terms mean. A lot of times, because the implementation details are hidden from the developer, in other words, you don't get the ability to really do anything with them. The language designers have already done that. You don't necessarily, a lot of times the way that you, the programmer, choose to use that language's representation of a data structure is that usage. So for instance, we'll talk a little bit in a minute about queues. Queues are not necessarily a data type, say in Go or JavaScript, but you can create them using artifacts that are already present in the language. So let's talk a little bit about some of the types. So we have an array, which is a collection of 0 or more elements accessed by an index. So I have a visual representation of what that looks like over here. So essentially what that means is that this you can imagine something inside of this box. And if I wanted to know what's inside of this box, I would ask the program to give me whatever element is stored at position 1, or its index value. Different languages will arrive at that differently. Again, a little bit beyond the scope of what we're doing here, but I strongly encourage you to, like I said, read the language spec to better understand your language's implementation of those structures. So it is a fundamental data structure for many other data structures. It's a core component of many different types of data structures. Lists are an example, dictionaries, strings, and so on. They are fixed or static in size and capacity, meaning that each time that you want to add something to them, they have to be recopied in memory every single time. So they can, sure.
Oh, sorry, I just wanted to ask you, because
please.
your diagram of an array is starting with 1. I'm more familiar with 0 index, or does that vary?
No, that's a great, yes, that it does, and that's an excellent question. Yes, normally they should start at 0. I grabbed this off of the internet without looking, so thank you for calling me out on that. But yes, normally most languages do start with an index of 0. Yes, that is a great question.
I forget, it's been a while, but doesn't Python start with 1? I think Python might.
It might. It's been a while for me with Python as well, but that might be. I do know it varies between languages, so it's a good possibility that Python, I know Python does a lot of things differently, so it would be likely that that's one of them. So yeah, but yes, thank you for making a note of that. That's very important, yeah. So there is the concept of a zero-based array, and then there's the concept of a one array, which is, like he said, where it starts. Like I said, they are fixed in static, they are fixed in size and capacity. You reallocate memory each time, so they can be, and so what I mean when I say they're fixed, once you create, again, generically speaking, once an array is created, it's essentially done. You can't add, remove, or anything else. In order to accomplish that, you copy the array to a new position in memory, you put another piece of data or another element into it, and you go on about your merry way. Linked lists are also another important data structure. They're the foundation of many more complex data structures. They don't require you to reallocate or reorganize on insertion of new data, so they're a little more sophisticated than the standard array. Each element is linked to another element in the data structure, and the key takeaway from these is that you can insert and delete at any point in the data structure, so they are not what would be referred to as immutable, which is a term meaning that they can't be changed. They are in fact mutable. They can be updated, assuming that your language provides the appropriate mechanisms for you to do that. So then the last one that we're going to talk about are queues and stacks. Queues and stacks are a special kind of data structure. Typically they're used for distributed systems and things like that. They're denoted by their FIFO, first in, first out, versus FILO, first in, last out. I'm sorry, did you have a question? Oh, okay. So yeah, FIFO versus FILO, essentially meaning, so we'll use FIFO as an example. So if you inserted an element in a position here, it would be the first element to be retrieved by whatever system was accessing it. Same for FILO. That becomes a lot more important when you start looking at things like networking, when you start looking at things like distributed systems and things like that. Amazon has a service called their simple queuing service that if you have access to that, you can play around with and get an idea of how queues and things and stacks work. Like I said, there's special types of arrays. They're designated by how data enters and leaves. They're implemented based on the requirements for data accessibility. So again, you as the programmer make a conscious decision on what kind of data structure you feel like you need. Then you take the steps to implement that. A lot of times they're useful in asynchronous systems. So asynchronous would be something like, I put this data here. I don't care when you come and get it, just that you come and get it at some point and you let me know. And then I just go on and do other things while you come and get the data and do whatever you need to with it. So those are one really good example of when you would see a queue implemented. So let's talk a little bit about the linguistic differences in their implementation. And I really want to clarify the technical definition here because this is where it really starts to become very language dependent. So for example, Python refers to what their linear data structure, which in a lot of other languages would be called an array, as a list. The reason why they do that is because it's more similar to a linked list. They decided that because of that similarity, they wanted to be different and refer to it as a list. So that's where that terminology comes from. This is their primary linear data structure. And because it's dynamically typed, it can be any type of data that you want. When I say that it is their primary linear data structure, one thing to call out about Python is that it allows for significant modification of a list. It allows you to do a lot of things like add at the beginning, remove at the end, do different sorting mechanisms and things like that. It allows for a lot of flexibility that a lot of languages may not have based on their implementation. JavaScript is another example. They refer to them as arrays, but again, this diverges somewhat from the technical definition because the language designers under the hood have already done a lot of that work for you. So it would be, I think, fair to say that it's relatively rare that you would ever want to worry about, well, let me back up for a second. It's rare that you would ever be in a position, at least in my experience, and take that for what it's worth, it would be rare for you to be sitting down and think, oh, I really need to implement a linked list or something like that. More typically, you're just going to say, I need an array or whatever this language's equivalent is, whatever that language's linear data structure is, and use it. But yeah, and then again, JavaScript being untyped, it can hold anything you want, similar to Python. Golang is a little different. It has two types of linear data structures. One is called a slice. That is analogous to the Python list or the JavaScript array. It's not fixed in size. It can grow as large as you need it to. The developers and the implementers of that language have done a really good job of hiding a lot of what I call the plumbing from the developer, so you don't have to worry a lot about what the implementation looks like, but you're able to use it pretty effectively. They do also have arrays, and these do follow more closely the standard convention for an array, which is that they are of fixed length and capacity. So if we go back to the preceding slide real quick, just to clarify what I mean when I say length and capacity. So the length of an array is how long, literally how long it is. The capacity is how much of something that it can hold. I didn't think to put an example of that in there, but we can mock one up in a second if there's questions around that. Typically, at least in JavaScript and Python, you don't need to worry about any declarations ahead of time, and really Go, you don't either. But it is there if you want to use it. And they do discourage that usage. But it, like I said, it is of a fixed length, it is of a fixed capacity. Again, it must be declared before use, and it can only contain the data specified by the type of the data structure. So to give you a little, can everybody see this okay? Because I'm not sure how that's showing up for y'all. Okay, let me see if I can. So Python, we have a sample list here, so you can see that I've named this list sample list. This is the syntax for declaring a linear data structure in Python. And then as an example, I've used the append method, which simply means take this element and put it at the end of this list. The nuances of why you would want to insert certain data in certain places and things like that is a little bit beyond the scope of this, but as with everything else, if you have questions, I can certainly talk to y'all about that at the end. And then you can see here I've given you an example of what that print statement looks like. So we've appended an item here, we print it, and we see now that inside of this list there is an element called cat. The same goes if I were to say print sample list index value 0. To clarify, that does seem to indicate that it doesn't start at 1. So print sample list index value 0, cat is the element that we get back. Now, one thing to note, this is not the same as this. Cat here is an element within this data structure. They are not the same thing. This is wholly different from this. That's why I did the print statements, to illustrate sort of that difference. So cat is contained within this data structure. Cat is the element itself. So I wanted to make sure to call that out. So line 12, we have a node example. And I did put the versions in there because, at least with Python and I believe Node as well, there are some nuances between various versions. So, and all of these examples will be available on GitHub once I get home and upload them, so you're free to go grab them if you want. So here you can see it's very similar to the preceding examples. We declare a variable called list. Same syntax as Python. Again, why I wanted to call out that there are language implementation differences, because if you're coming from Python to JavaScript, you may be sitting there for a while trying to figure out what a JavaScript list is, because that data structure is different. So we call this sample list. Now, one thing that I've done here is I've tried to honor the language's syntax guide. I call that out because me personally as a developer, if I'm going from one language to another, I try to follow their stylistic guides to the point where I'll refer to things as the same. Like I'll refer, if I'm talking to someone about Python, I'll say, something about a list or a dictionary. If I'm talking to someone about Go, I'll talk about maps and slices and things like that, just to keep in my head that there are these differences and that you should be working within their ecosystem, not against their ecosystem. So we say here, there's their example. So here, as you can see, this is append, this is push. So this goes back to what I was saying earlier, where you really, really have to look at the language's implementation and the way that the language wants you to interact with these data structures. So we say push this element into this list, and then we print this, and you can see here the same as with Python. The output is the same, but the way in which we arrived at that output is much different. And then again, the same thing down here, we access based at index 0, so we are essentially saying, in this array, give me the item that's at this index, and we see that that is, again, cat. And then Go's version is, again, a little more complicated. We've created a variable called sample list. We've defined that as a list, or I'm sorry, as a slice of type string. So this slice can only ever contain strings. If you try to put an integer in it, the compiler will yell at you. It's a really good self-check. So we say here sample list. There are some nuances to the Golang append function that I won't go into here, but that's suffice to say there is a reason why it looks much different than the push or the append methods from Python. So we're saying that we're taking this data structure and we're putting the element cat into it, which of course is a string. We print that and we would see, we print that and we see that we're getting back the data structure containing the element cat. And then we can see down here when we access that, again, very similar syntax notation for the accessing portion, that it is cat that is returned. These are relatively, you will start to see that there are some similarities as well, mostly because of the ancestry of the programming languages, but histories of programming languages is a really fascinating topic if you haven't gotten into that. Oh, sorry. Yes, sorry, I didn't see you back there.
What does a declaration of an array look like in comparison to a slice in Golang?
Sure. So, great question. So you're essentially declaring the size and the capacity ahead of time. This is only declaring, I believe this is only declaring the length. And I can actually send you this article. It's really, really fascinating. It's a really great explanation of why they made certain design decisions and things that they did. But essentially what you're doing is you're creating ahead of time the length and the capacity of the array, which is I'm sorry. Oh, I didn't write that. Sorry, I can see if I can zoom in. It's on, yeah, if you can zoom on Zoom, that'd be great.
Can you zoom on Zoom?
I don't know. So here, I can do this.
The URL bar right there.
Actually.
Click on that link.
Oh, it's on yours. It's whatever.
So let's do this. And that may not be much better. View. I was hoping there'd be a zoom feature here, but I don't.
Yeah, right there.
Where? Sorry, I'm not.
Those options and appearance.
Yeah. Control equal.
There we go.
There we go.
There we go. Is that better? Everybody see that? Okay. Okay. Cool. Yeah. No problem. Yeah. So this is the short form syntax. This is the short form declaration syntax that I was mentioning earlier. The main reason why, since we're diverging on this a little bit, the main reason why you really don't want to use these in Go is because once you declare a length and once you declare a capacity, you're done. If it grows beyond that, it's an out of bounds error. It's really bad. Don't do it. They give you slices for a reason. And I don't mean that sarcastically. I mean that literally, if you go read that blog post, they tell you that. They literally say, we give you slices for a reason, please don't use arrays, only if you absolutely really, really, really have to. And the reason why is because they've done a lot of really interesting optimization internally, where they basically, so the memory allocation and everything that I was talking about earlier, they do all that for you. It's really cool. Sorry, I really like Go. But yeah, so they do a lot of really interesting optimizations and things like that. So that's why I was a little rusty. And I'm glad that you made this, I'm glad that you asked, because it's a great question. It really is. But that's essentially what the difference is that you do declare that length and that capacity ahead of time. Now, what I mean when I say out of bounds errors and things like that, I mean if I tried to put 5 of something in here, it would not go well for me. And that's just a limitation of the language. Again, I can get more into that, but being that this is a beginner class, I don't want to digress too much. But essentially, you can, like I said, just essentially say that 4 good, 5 bad is the easy way to put that. So okay, so we've got that now. Sorry, 1 second. We're trying to get back to the PowerPoint here. Okay, cool. All right, awesome. Yeah, no, Go does a really, so in a very, 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 very short nutshell, basically what Go does is they take the array that's in memory, copy it on your behalf, do everything that it needs to be done, and then they just give that back to you in the form of a slice, which is why they call it a slice and not an array, because it's literally a slice of an array. And if you look at some of the examples and things that they have, you can actually see how that's represented in memory and how they actually go in and divvy it up and do some really cool, and I mean literally, that's literally why it's called a slice, is it's a slice of an array. So it's pretty neat stuff. See, told you I love data structures. So let's go on to the next one. Okay, I think. Yeah, sorry, I got to get back to where I was. Okay, cool. So last but not least, hash map data structures. Hash map is a fancy term. It essentially just means it's a key value pair store. It's a structure that maps keys to elements. There's a lot of math and a lot of computer science and other stuff that goes into that mapping and everything, but I won't bore you too much with those details. So it's not quite the same as something called an associative array. It's close. Again, that's a lot further down into the weeds, but it is an implementation of an associative array. This, more than anything, I think, besides maybe with the exception of arrays, and even then I think that this has more nuance, this terminology varies very, very heavily between languages. I see you nodding your head, you know my pain.
Dictionaries, maps.
Yeah. Go is not immune from this. I will, throw them under the bus when they deserve it. They called it a map because sometimes they're called maps, and because they, I guess, thought that was a more accurate representation of the data structure. One thing you'll notice a lot in computer science, at least from my experience having a political science background, there's a lot of philosophy, believe it or not, and there's a lot of personal opinions that get put into things. Python is a fantastic example. I won't go too much into that, but just something to be aware of. If you're scratching your head wondering, wait, why did they do this again? Just know that sometimes it's because they liked it that way. And that is literally the answer, is because they liked it that way. Why is Python 4-space indents? They thought it was more readable. It doesn't make the program any faster. It doesn't make the program run any better. It looks clean. And it does, but that's an example. So, like I said, terminology varies between languages, but more often than not, the use case doesn't. So as an example, I've given you some of the terminologies that I've seen in different languages: hash tables, hash maps, dictionaries, associative arrays, and it keeps going. So before we get too far down into this, let's talk about what a key is, the key component of a key value pair, pun intended. So a key is pretty much anything. In most languages, it's whatever you want it to be. It can be a string, it can be an integer, it can be, it depends on the language's implementation. More often than not, they're going to be strings. And the reason for that is because you want it to be something that you can remember and that you can refer back to later. They're user-defined index values. So they are arbitrary, but they do have to be unique. And I'll get more into that in just a second with our example. Let's talk, and then the other component of a key value pair, of course, is the value. These are arbitrary, but they do not have to be unique. That's a very important distinction. They are accessible via this user-defined index value, a key. So let me break that down. When you saw me using the number 0 to refer to an element in a list or an element in a slice, you can do that same syntax with a dictionary or a map or anything like that. If I know that this is I know this is 1, 2, 3, I can access it in just the same fashion. And I'll have an example of that in just a second. So like an array, they can hold any kind of data supported by the data structure. Python doesn't care. JavaScript doesn't care. Golang really, really cares a lot. So the language spec determines the kind of data that can be contained. I'll just leave that at that because I don't know of any, off the top of my head, examples where that would not be true. Okay, so let's talk about linguistic differences in hash map implementation. So Python, here they're known as dictionaries. Do not go looking for a dictionary in JavaScript, you will be disappointed. They are functionally similar to other implementations and they can hold anything that you want. Python is renowned for its flexibility. That's a recurring theme if y'all haven't noticed that yet. Python loves being flexible. It both is a great thing about the language and it's a bad thing about the language. But it is a very, very good language for beginners because it makes things incredibly straightforward and incredibly easy and it doesn't restrict you, which is, I think, its most important aspect. So Python, we've got a dictionary here called sample_dict. Now again, this is Python's preferred syntax for naming things. We define this, it might be a little hard to see for those of you in the back, but this is what we call brace syntax. It is different. It has these neat little outcroppings on the left and the right side here. And then we put inside of that, so again, you see we can, now this is just frankly something that you have to remember. I don't know of any other way to put that. You can't access a dictionary, at least as far as I know. If someone has a different example, please correct me. But as far as I know, you can't access a hash map type data structure with brace syntax. You can only declare it. I honestly don't know why that is. I'm sure someone somewhere does, but I am not that person. So sample_dict, we take the key animal. So here, this is what our key is. This is how we're going to refer. Oh, I forgot something. Sorry. I forgot my good versus bad example. I apologize. Got ahead of myself. All right, so real quick, before we get back into that, give you a little bit of whiplash, let's look at a good example versus a bad example of how we declare an array. So, of a hash map. Way too much terminology. So line 3, we have a variable D1 that's assigned to this, we're just going to call it a dictionary for simplicity's sake. So we're going to assign D1 to this dictionary. Now, you can see here that this key and this key are unique, meaning that if I go in later and I say I want the data value stored at 1, 2, 3, it's going to give me back my name. If I ask for the data value at 4, 5, 6, it's going to give me back Mary Sue. If I come down here to line 11, I've declared a similar example, but this one is bad. This is why it's bad. If you ask a computer, or frankly, you, which employee am I referring to, you're going to look at me and go, there's 2 of them. Why not both? Or more likely your computer is going to yell at you and say you've done a bad thing, please don't do that. And so that's where if you were to print this out, it would essentially barf and give you a big nice long exception, or depending on the language, an error or something like that, where it basically, the summary of it is, you've used your key twice, don't do that. Now, one very subtle bug that I am guilty of, and I will fully admit that I am guilty of this, is if you are assigning elements in a for loop and you are using a key and that key is not unique, what will happen is, at least in Python and a couple of other languages, it will do what you tell it to. It will reassign employee to whatever the next data element is that you're providing to it. So if you think it's Joseph, it might well be Mary Sue, it might be Bob, it might be something else. So that's why index values are critically important, especially in hash maps, because the biggest, most prevalent use case of these is in REST APIs, JSON, formatted data and things like that that are completely arbitrary and that you have full control over. So going back to what I said earlier, names are extremely important, index values are important. If you find yourself having some trouble, make your data structure more complicated. That's okay. Don't make it so complicated that it's impossible to use, but you can introduce some complexity and things like that, and I'll show you an example when we're at the end of the talk. So to get back to the linguistic differences. So like I mentioned with Python, you can see here, we access it using the square brace syntax. We get this value, we assign this value to this key. We print that, again, like I said with the array example, this is a dictionary, this is not the individual elements. So I've got a key value pair stored inside of a dictionary. The key is animal, the value is cat. This can grow arbitrarily large. I'm sure there's some limit somewhere, but for most purposes, you're going to be just fine. And again, much like with the index syntax, because of their origins and because of a lot of other reasons, they're accessed almost exactly the same. The only difference is rather than an index value, an integer, you're using an arbitrary string. Now, again, if you wanted to, you could use integers yourself, but at that point, you should probably use an array, just because it's simpler, and that's in keeping with sort of the paradigms of the language. Node.js, it's a similar example. Now, Node is a special snowflake because they refer to them as objects. I have no idea why. The only thing, I have a couple of working theories, but and again, anybody who's a Node.js developer, please keep me honest, it is not my strong suit. But I've never found a good reason as to why they call them objects. That is where the O in JSON comes from, JavaScript object notation. So again, defined very similarly with the exception of the keyword var. Brace syntax, we've now defined that this sample object variable is going to be a dictionary. We alternatively can also define it using the new keyword and then declare an object. So we either one of these are functionally the same. 16, we again assign it in exactly the same way as Python. We simply say this key is assigned to this value, cat. And then again, we access it much the same way. Console log shows us the dictionary or object. The line 22, accessing the key animal, gives us back the value cat. Golang, again, a little bit more complicated, but essentially what you've done here is you've taken a variable sample map, we've instantiated it. Go is unique because it requires initialization of a map prior to assignment. See me after if you want to understand that a little bit more. Or we can also define it using a more traditional syntax, which is map, data type. So either one of those are extremely equivalent. It's just syntactic sugar. Assignment statements, again, very similar. You take the key, you assign it to the value, you print it, you get your map. Golang prints it out a little bit differently. It actually tells you that it's a map, and then it gives you the elements that are present in the map. And then again, for slice, for retrieving an element, very similar syntax. You access it based on the key. So those are hash maps in a nutshell. Again, to bring it back to sort of a more technical or a more applied view, these are probably going to be your bread and butter. I use slices a lot, but that's because of the type of data processing that I do. If you're working in REST APIs, if you're working in web development, anything involving JSON, anything, you will be very familiar with whatever your language's implementation of hash maps is. They're also the developer's tool of choice in data structures a lot of times because they are arbitrary. I can design my data structures. I can make the keys what I want them to be. I have a lot of control and a lot of flexibility, which is really desirable. So, in conclusion, data structures in modeling data are a critical feature of any modern programming language. Computers take in input and they output. That is what they are designed to do. Data is a key integral component of that since it is the input and it is the output. Many of the implementation details are abstracted from the developer and only their functionality remains. So like I was saying earlier, if you go look for a linked list or you go look for a stack or a queue or something like that, a lot of times you won't find it. You'll find an array or you'll find a slice, and it's up to you, the developer, to use that as a stack or to use it as a queue. So I urge you to familiarize yourself with some of those terminologies and some of those in a lot more depth. Like I said, learning how to use data structures effectively makes for efficient, maintainable, and readable code. It's much easier to use code that is well structured, that is presenting its data in a logical and consistent format. Though the different languages use different nomenclature, these data structures exist in almost every modern programming language. They are fairly ubiquitous. It's just a matter of figuring out what does OCaml call this versus what wall code, I don't know, Sure, wall code, we'll go with that, which is a real programming language, by the way, if you've never seen it. It's really fun. It's exactly what it sounds like. So like I said, the nomenclatures are different, but they're definitely going to be there. You just have to figure out what they are. So some typical use cases for data structures, this is an example. Persisting data for later reuse in the program, that sounds pretty straightforward, but it's extremely important. Again, if you don't save, the processor isn't going to do it for you. So if you don't say, keep this until later, it's gone. If you're in a for loop and you're generating all this really cool data and you're super excited about it and you don't put it somewhere, it's gone. Sorry. So data structure is super important. Generating a structure on which some action should be performed. So think REST APIs, things like that. Something where you have a contract with a user where someone is asking you for something and you're going to give it back to them. You have to structure it in a way that they can access and understand and everything like that. So building out a data structure and then presenting that to a user is really important, especially if you start getting into REST API development and things like that. That becomes, I would say, critical at that point. And then, of course, as always, with anything in computing, there's a lot more where that came from. There's composite data structures. JSON is a great example. I didn't really go into it in very much detail, but databases, data persistence, obviously, you've generated all this data, you've done a great job of constructing it and structuring it and modeling it, and then your program closes and it goes away and you're really sad. Put it in a database, you don't have that problem anymore. And then as I promised to show you kind of an example of all of these put together, this is a JSON example that I mocked up. So you can see here that this is an object-noded device, or I'm sorry, an object-noded structure. Most modern languages, I would say most modern languages are going to handle JSON in some shape, form, or fashion. So you can see here we've got an arbitrary key, an arbitrary value, an arbitrary key, an arbitrary value. Now, one thing that I do want to call out is here you can see that this key is assigned to an array. This is going back to what I was saying earlier, where you can start to build more complicated data structures. If you find yourself in a position where you're like, well, an array doesn't really work for this and a dictionary doesn't really work for this. Well, again, they're like Legos. You can build what you need to out of them. So you can see an example of that here. And then you can see inside of this array, we've put another object, which is key, value, and then another nested data structure of a list with various programming language versions embedded in it. And so that's how you can get away with using something like name here and then using it again down here and not get yourself into trouble, because this is not the same as this. This is inside of this data structure, which is nested inside of, which is assigned to this key, which is in this same object. I hope that makes sense. I didn't do a very good job of explaining that, but yeah. So that's kind of an end state. It can get much more complicated than this, obviously, but that does show you sort of how they can be assembled into really cool stuff. And that's all. Any questions? Cool.